Hi everyone, we'll start it in 3 minutes at 5:05, 6:05, sorry. Before we begin, does anyone have questions on the material covered on Monday? Any questions at all? Okay, then I am just going to remind you all that your assignment is due April 26th at midnight. So I'm just going to show you the calendar. I'll share my screen. So we've gotten through chapters 1 and 2, and we're working on chapter 3 until the end of next week. And so at the end of next week, April 26th, your assignment 1 will be due at midnight. Okay, so just a reminder for everyone. And then we'll hop into chapter 3 again, unless anyone has questions now. Okay, again, if I'm talking too fast or not loud enough at any point and you want me to repeat myself, please let me know. Okay, with that, I will begin. Remember Monday, I guess, we were starting chapter 3, randomization. So we talked about what a randomization is, why it's so good. So recall that the problem with just any analysis without randomization to begin with. So suppose we have just an OLS regression where we want to look at X on Y. Normally the problem is when we're comparing across a whole range of people, there is some sort of thing called selection bias in our estimate because the people who receive treatment, they might be somehow different from people who don't receive treatment. And that component is biasing our estimate of our true effect that we want. So in practice, we need to find some sort of method to eliminate the selection bias. So as we talked about, randomization is a really good way to do so. So economists have called randomization the golden standard of impact evaluation. And that's because if you implement this methodology, you're basically guaranteed to have eliminated selection bias. So that's great. So that's why it's such a really solid way to estimate an impact evaluation. However, also note that it's more expensive than other evaluations, so other retrospective analysis. We've talked about the difference between prospective and retrospective, remember? Do you guys remember that? What's prospective and what's retrospective? If anyone wants to answer in chat. Yeah, remembers, but what is it?
Can I answer it out loud?
Yes.
Oh yeah, retrospective is when you do it like with the information you already have, like after the program, and prospective is like before the program, so you can decide better the control and the treatment group, and well, how these and all the variables that can search during the program.
Exactly. Thank you for answering. That's perfectly correct. When we have prospective analysis, we normally start the investigation at the same time that the program is being implemented. And with that comes a lot of valuable data. So for example, randomization is a prospective analysis because we have that data of our treatment and control groups before they're even treated. And that allows us to ensure that our two groups are very similar in characteristics and that the only difference between the two groups is the treatment effect. So then any difference in our outcome variable y, we can attribute to that treatment effect, right? Because when there's differences between the two groups, even before one of them receives treatment, it's really hard to say that in the end, the difference is only attributed to the treatment because to begin with, there was other things that were different, which might also affect the final difference. But retrospective, we're using already existing data, so we likely don't have that baseline data before treatment, and it makes it harder to find a good counterfactual group or make sure that the two groups are balanced. So that's why randomization can be said to be better than other retrospective analysis, but remember that this is more expensive. So from an implementation standpoint, economists aren't always going to want to implement randomization because it's expensive and they might not have funding. And maybe you're able to use a retrospective analysis that is less precise but gets you very similar estimates. So then you're better off using just a retrospective for faster and cheaper analysis. So that's a consideration. And then also we talked about publication bias, how randomization really removes publication bias. Just in general, when you're publishing papers in economics, there's always a publication bias because maybe publishers or journals have a preference to see some types of results. Or for example, commonly when economists are making a randomization or this program, they usually work together with some sort of government or non-governmental organization to fund the project and to actually implement it so that the organization can carry on the project in the future and the economist can leave. So there could also be some sort of bias from the organization that they are working with. If they prefer to see some sort of results over the other, there could be bias there. But in general, randomization reduces publication bias compared to retrospective analysis because it's such a foolproof method. It's really undisputable what results you get because you can't say that the methodology isn't good if you can say we randomized and the treatment groups and the control group, we can show that they're balanced. When you can show that they're balanced, then you can for sure 100% say any difference in the outcome variable is attributed to the program. So then if you have a weird result, so if you have a result that is not intuitive, it's opposite from what you hypothesized, for example, it's more likely to be published in a journal anyways because it's more credible. Whereas in comparison, if you have a retrospective analysis, for example, a difference in differences, and you get a counterintuitive result, so maybe you find a negative effect when you expected a positive, the publishers are more likely to say, no, we're not going to publish that. We think there's bias in your estimate. You need to go back and change your strategy. And that's just because they're less likely to believe your results. So with randomization, you don't have that problem really. So it's definitely easier to publish when you have a randomization in your design. So keep that in mind if you want to be published. Okay. Okay, and just recall that the reason why randomization removes selection bias is because recall that we're putting people into a treatment group and a control group. And the selection bias comes from the fact that the two groups are different to begin with. So if the two groups aren't different to begin with, then we can't attribute the treatment as the causal effect. Maybe there's something to begin with that's different and that's driving the effect. That's the selection bias. So randomization ensures that we don't have selection bias by making the two groups look identical on average. So to say that they look identical on average is to make a bunch of different, or to take data on a bunch of different characteristics of the treatment group and control group. So what kind of characteristics would you guys include, do you think, if we had to compare a treatment group and a control group to see if they're similar? What variables would you look at? There's really no wrong answer, so don't be afraid.
Maybe age and culture.
Yeah, for sure, age, gender, education, how many years of school you have. It could even be, are you working? Are you married? Do you live in a house? Do you live with your family? How many people in the household? Yeah, socioeconomic level. Yeah. So some sort of indicator for your socioeconomic status. So income level, or maybe there's a poverty index. Those are all really good. So if you have a poverty index from 0 to 1, what is your household's level? Basically any descriptive characteristics that we could compare between the treatment group to the control group. And we want to see that on average, the two groups are identical. And it's not identical, it's statistically identical. So then we fail to reject that they're different using a test. So yeah, those are all good things to include. And that's basically how we checked that this is our assumption basically. Our key assumption of the randomization is that we remove the selection bias because we randomize, so the two groups are balanced. And so we can check that, we can test that. And how we test it is through comparing these characteristics between treatment and control group. So this is a methodology that you're able to test the assumption, which is really great as well. And that also strengthens the validity of a randomization. It's because it's testable, the assumption. So yeah, if you read any randomization papers in economics, table 1 will always be this balance table where it shows either the mean characteristics for the treatment group and the mean for the control group, and maybe a test whether they're statistically different or not. And that's really important because that shows us whether or not we should believe their results. If they randomize and somehow variables are different, so it doesn't randomize the characteristics very well, then we might be concerned that these variables are still affecting our outcome. And then you kind of need to use your economics brain and think whether this variable that is slightly different between the two groups, how it might affect the outcome. If it's not important or not relevant, then you don't really care. If it is, seems like it's really important to the outcome, then that's a problem. And we need to make some actions about that. Okay, so just remember this equation. This is the assumption, the independence assumption, which is the only assumption of randomization. And it's saying that basically treatment status isn't determined by your baseline outcome. So you can see here in the right-hand side, these two, the EY0I given DI equals 0. That's saying your outcome if you don't receive treatment if you're in the control group. And then this below, EY0I given DI equals 1, that's your outcome if you don't receive treatment if you're in the treatment group. Is it okay to keep randomizing the groups until you have a statistical identical group? Okay. Good question. Someone asked, like, if you don't have a perfect randomization, where some variables are not randomized perfectly, can you just keep randomizing until you do get identical groups? Yes, that's normally what economists do, I believe, because nowadays you're just doing it on your computer and saying treatment and control. And if you already have survey data, you can easily tell whether the groups are balanced. This wasn't as common back in the day, I'm not sure. Maybe they just didn't have baseline data to begin with. But yeah, also if you're really concerned about some variables, there's other methods we can use, such as stratification, which we'll talk about later in this chapter. But yes, that's definitely a possibility. Yeah. So, yeah, so recall that these two are our baseline outcomes for our treatment and control group. And right. And so they should be equal. That's why you can replace this for this. You can replace line 1 with line 2 because we're saying that randomization ensures our baseline characteristics are equal between the two groups on average. That's why you can replace the first line with the second line. Is that clear or no?
Can you repeat, please?
Yeah, I'll repeat it. So we can replace the first line where we say, this is our basically observed outcome, right? Our difference. So we have the expected outcome of the treatment group minus the expected outcome of the control group. That is equal to, normally we have the expected outcome, like if the treatment group is treated. So that's expected value of Y1I given DI equals 1. That's our treatment group receives treatment. And then subtract the expected value of Y0I given DI equals 0. So that's the control group doesn't receive treatment. So that's as we expect. That's what we observe. Normally comparing those two might create a selection bias, but in this case under randomization, we don't have selection bias. And that's because we can switch this term, the EY0I given DI equals 0, for this term below. And that's because we're saying these two are equal on average. That the average baseline, so that the average baseline outcomes are the same for treatment and control group. And that's the characteristics table that we were just talking about. That each characteristic is equal on average. Okay. So that's the independence assumption. And basically, your baseline outcome, so Y0I, your outcome when you don't receive treatment, is not dependent on your treatment status. They're independent. Okay. So yeah, that's why randomization removes selection bias. And an example of that, remember how we talked about how we want to know the effect of going to the hospital on your health. Okay, so the problem with that, if we just run a regression of going to the hospital on your health, remember that your baseline health is going to affect whether you go to the hospital. So if I'm sick, I'm probably going to go to the hospital more than if I'm not sick. So that's the selection bias, because sick people will go to the hospital and then our result will be biased. Our estimated effect will be biased. So with randomization, we're saying that, okay, we're telling people whether or not they can go to the hospital, and it has nothing to do with their baseline characteristics. So it doesn't matter if you're sick or healthy, we're randomly putting you into treatment or control group. And so then if you're sick, it does not determine whether you go to the hospital. So that's how you remove selection bias. Okay. And so with that, since there's no selection bias, we're able to run a simple OLS regression and find causality, right? So then we have our yi is our outcome variable, is a function of a constant term plus our treatment dummy. So di equals 1 if the individual receives treatment and 0 if they don't, and then your error term. So it's really simple because our treatment dummy is the only explanatory factor of our yi when we randomize. So when we randomize, we only need to run an OLS regression and we will have causality. This isn't always true if our randomization is imperfect. It might be beneficial to add a control if one variable is not balanced. But it depends on each context. Normally, this is sufficient. Okay, and then in just expectation terms, what we estimate our beta hat, that's our estimated effect, is the estimated average of our outcome given di equals 1. So the outcome for the treated group minus the average outcome for the control group. So it's just the difference in outcomes between the two groups in average outcomes. So basically this is telling us that when a randomization is correctly implemented, we have an unbiased estimate of the impact of the program for our sample. So this is the average effect we estimate for our sample of study. So in other words, this estimate is internally valid. Have you guys heard of internal validity? What do you think it is? Cuéntame. What do you think internal validity is? Nicholas says internal validity means that the results for the particular subject work well. Yeah, that's correct. So within our sample, we're saying that our internal validity is that the assumptions of our randomization are true, which allows us to obtain causality. So the internal validity looks inwards into our sample and looks whether the methodology allows us to obtain causality. Consistent estimator, that too, yeah, so consistent, yes. So yeah, it's looking inwards within our methodology because it's basically testing our assumptions. So if our assumptions are true, we're able to obtain an unbiased, consistent estimator. Okay. So now we're going to talk about randomization in practice for a moment. So sometimes, normally, if there's this program, say you need to define eligibility, right? Eligibility says who is able to access this program. Because remember, we only want to compare eligibles, we only want to compare within the eligible population. So we want, within that eligible population, we choose a treatment group and a control group. But we don't want to compare eligible people to non-eligible people, because then we would assume that there's critical factors or variables that are different between people who are eligible and people who aren't eligible, right? So if this is a program for people with a poverty index or poverty that's really low, so they're more poor, you don't want to compare them to richer population, because they're going to be different in other ways than just receiving the treatment. So that's why you define an eligibility, and within that eligible group, you then randomize. So that's really important. Of course, when you define a program, sometimes the amount of eligible participants, the amount of people that are eligible for the program, is larger than the spots available for the program, right? So if you define eligibility, say their poverty is below the 50 on the index. So if we have a poverty index from 0 to 100, anyone below 50 is eligible for the program. But there's only 1,000 spots, and below that cutoff, we have 5,000 people. So what do? Then there must be a decision about who will enter the program and who will not. So that's a really good opportunity for randomization, because then you can use this as an experiment. So Progresa, now called Oportunidades, is an example of this. I believe it's in Mexico. Oh yeah, it says here. It's in Mexico, and the program offers grants to women. So basically money or a scholarship or a beca, something like that. So this is conditional on their children going to school and also receiving some nutrition supplementation, healthcare visits, and participation in health education programs. So what this is saying is that the government is giving these mothers money, which they're expected to spend some of it on their children for nutrition and this health. So it's not that they just get this money and can do whatever they want. There's some conditions, right? That's why it's called a conditional cash transfer. Okay, so this program offers conditional cash transfers to mothers. But due to budget constraints, they couldn't offer it to everyone, every mother that wanted it. So they decided to use a randomization in this moment. It's a good opportunity. So they randomly implemented the program in 506 communities. And this is really to be fair, because think of if you have an eligible population and that's larger than the people that you can give the program to. Is it really fair to say, oh, I'm gonna choose like who I think deserve it the most, or maybe people that are closest to me, or whatever communities matter the most to me? That's really not fair. And also, if these people are all within the eligibility range, it's not fair to say some deserve it more than others, because they're all within the qualification, so they should all deserve it. So the only fair thing to do would be to randomly decide who gets it. And then if you're randomizing anyways, you may as well be an economist and look at the effects. So that's what they do. So this program was evaluated through an academic institution. And yeah, they found it to be effective, but this is just one circumstance where it's an ethical question who you should choose to give the program to when there's more eligibility or more people who are eligible than spots, and randomization is a really good answer. Okay, another example of this is STAR. I'm not sure if you heard of STAR. It's a program, I believe in the 1970s, that was implemented in the United States. Their big question was they wanted to understand whether if you decrease the class size, would that improve learning outcomes? So the argument is if there's a smaller classroom, each student has more personal time with the teacher, so maybe they learn more and stuff like that. So previously there had been no experimental evidence on this. And interestingly, non-experimental research had shown that class sizes do not affect learning. So there's no difference whether you have a really large class or a really small class. On average, kids will have the same outcomes. If there's no effect, then they argue that schools should just make class sizes really large and just save money because they're reducing the number of teachers because it doesn't matter anyways. But that's a problem because with this non-experimental research, we're concerned about bias or selection bias. And if you think about it, normally weaker students or students that aren't as smart will be put into smaller classrooms so that they get more personal attention. So what these authors were really picking up was just that students with lower grades were being put into small classrooms and smarter students were in bigger classrooms. So then they say classrooms doesn't have a good effect on learning outcomes at all, or small classrooms. So it's not a good policy, but you can see how that policy recommendation could be bad and not true. Okay. So obviously the STAR program addresses this problem by randomization. So they have different class sizes and they randomly put students in different class sizes. Okay, so this was a really large program, I think across one state in the US, and it's about $12 million, and it ran for 4 years and involved almost 12,000 children, so it's really large scale. I don't think they make experiments like this anymore. No one really wants to put money into that. Okay. So as we just talked about, how do we check whether the randomization was successful? Well, we use a balance table and compare characteristics between the treatment and control group, right? Because with randomization, we expect all of these characteristics to be balanced. Okay, so look at the table. And you see there's 3 different classroom types. So the first type is small, the second type is regular, and the third type is regular with an aid. So this third type is basically saying that maybe you don't need a small classroom. Maybe you just need a regular classroom, but with an extra person to help the lower ability students. Okay, so what do you think of this balance table? So look at all the variables they choose. Free lunch is a dummy variable equals to 1 if the student receives a free lunch. And normally, basically only students with lower incomes or if they come from families with low incomes have access to a free lunch. So this is some indicator of the percentage of poor students in a school or a classroom. And then white Asian, they include this, so it's a dummy variable if the kid is white or Asian. And that's just because in the United States in particular, there's a big dichotomy or difference in learning outcomes between white kids and black kids or kids of color. And that's mainly due to systematic problems and the marginalization of colored people in the US. It's really awful there, actually. So yeah, they include a dummy variable for white or Asian because those kids are more likely to achieve better grades. Okay. And then just the age of the student in 1985, they want to make sure ages are similar across the two groups. And then attrition rate. Do you guys know what attrition rate is? Yes. Okay, well, I'll say it anyways. No. School abandonment at this rate. Okay, so attrition rate is a general term we actually use in economics when we're looking at experiments. So we use this in randomizations, and it's especially important when we're looking over a longer period of time. But the attrition is people who leave the survey or our study. If we have an experiment and we put people in the treatment group and people in the control group, we want everyone to stay with the experiment for the whole time. That's ideal. But for some reason or another, maybe some kids will drop the experiment, maybe because they moved to another city, or maybe some other reason they had to drop out of school. Whatever reason they had to leave the experiment, that's the attrition rate. So the percentage of kids that drop from the experiment. And do you guys know why that could be concerning? Any reasons? What do you think?
Well, in this case, it can be that it doesn't matter if you have like smaller or bigger classes. Like if people are dropping school, you're not going to get to anything.
Right. The thing is, it could be a problem because if it's not, the thing is we have randomization. And randomization is what we're saying is the important reason that we're eliminating selection bias. But after randomization, if kids drop out from the experiment, maybe it's not random, the kids who drop out. So maybe the kids who are less motivated or lower test scores, systematically, these kids drop out, whereas the high achieving students are more likely to stay in the experiment. Then this can be problematic because say all the low achieving kids drop out of the I don't know, say the big class size, because in the big class they're not getting enough attention and they can't keep up, so they have to drop out. Then we're increasing the average test scores of the big class size group, right? Because all the ones that are doing really badly have to drop out. So then they're not picked up in our analysis at the end. So then the control group looks like they're doing better than they actually are, because we can't have the data on people that leave the experiment, right? So that's the problem. It's lost data and we don't know what their outcome would have been. And so it might not be random who drops out. Another important example is that, for example, think of, if you think classroom size does matter. So typically people say small classes are better because you get more one-on-one attention from the teacher. Well, then if you have parents, for example, that are in the big classroom, they have kids in the big classroom and they really are motivated about their child's education, they will push to try and get their kid moved to the small classroom size, right? And so then all the motivated kids and parents are moving into the small classroom size, which will increase the average test outcomes. So then when you compare the effect, it looks bigger than it actually is, and that's because after randomization, there's selection bias by kids switching classrooms. That's not actually attrition, but that also would bias the estimate. But yeah, attrition is just when people leave the experiment, so we don't have data on them, which is really problematic. Okay. So someone asked, can you make different clusters with children with the same characteristics and then make the two groups? Randomly assign the same amount of children from each cluster. Then you make sure it's balanced. Yes, you can do that. That's called stratification. We're going to talk about it today or tomorrow. And that's what you're doing. You're choosing variables and randomizing people within that variable. But that's not, I mean, that wouldn't change the problem of attrition, but yeah, you can do that. I mean, attrition is just lost data because these people are leaving, so we don't know whether they're leaving randomly or if it's systematic. And if it's systematic, we're creating bias again. Okay. So back, and then we have class size in kindergarten. So we want the small to be different from regular. And then these two should be similar. And then the last one is percentile score in kindergarten. So that's kind of just like supposed to be a baseline indicator of test score ability. And they want that to be balanced too. Okay, so what do you guys think of the balance table? Does everything look balanced? Or are there some variables that aren't? Okay, so I hope you're looking at it, but you can see this joint p-value test. If they're statistically, I can't talk today. If they're significantly different, then the p-value will be less than like 0.10, right? Oh, sorry. You have a question about the final exam? Okay. Someone's asking if these papers are going to be considered on the evaluation of the exam. Probably not. I'm not going to ask like specific details like, oh, was this table balanced? Because, well, one, it's going to be open book, so anything in your notes you'll be able to go back to. So I don't think there's much value in just making you go back and check that. But I mean, it's good practice because I will ask you similar questions probably about using new tables. So you need to understand how to interpret these things. But no, I wouldn't ask specifics about the papers in general, but you should cover them. The sample that is used for randomization has similar characteristics between the individuals. That's what we're asking, yeah. Sorry, I'm not sure I understand, but that's what we're looking at right now. And so we'll talk about how we can see that. So I'll answer that right now. Okay, so you see this joint p-value? If it's less than like 10%, then it's statistically different at the 10% level, for example. So you can see this free lunch. I mean, they're pretty similar, 47, 48, and 50. Like I wouldn't worry about that. But statistically speaking, they're significantly different. I don't think that would affect our estimates too much because they are very close. Okay, Maria asked why they use a variable white and Asian students. It's because it's a dummy variable equal to 1 if a student is white or Asian and 0 otherwise. And this is because of the United States context. In the United States, there's a big problem where children of color, so Black children, often have worse educational outcomes, and that's due to a long history of discrimination. So whatever systemic forces there are, Black kids on average do worse than kids that are white or Asian. So they're using white or Asian as a dummy variable because they think that these kids might perform better in school. So we want to make sure they're balanced between all the different groups. Okay. So yeah, we can see that this variable white Asian is balanced because the joint p-value is 0.26. Same with age in 1985. You can see here like 5.44, 5.43, 5.42. And then it's not, oh my God, I can't talk. It's not statistically different. And then the problem is attrition rate is, So you can see it's significant at the 5% level. And the small class size, the attrition rate is lower than the regular class size and the regular with aid. So like I said, remember my argument where if there's kids that have lower test scores and they're doing poorly in school, if they get put into the bigger class size, maybe they can't keep up and they have to drop out because they just can't do it. And that would increase the test score average of the control group. Yeah, so Jorge says this difference means that there is selection bias. Yeah, that would definitely be a problem. I mean, the different means. I mean, we don't know because we don't know what kids are dropping out, but it's definitely concerning. And if you do have attrition, you need to somehow argue that you think it would be random or attrition's really small. But in this case, attrition's really large. It's 53%. That's over half of your data being lost. So you would be concerned that you're reintroducing bias into your estimation. Yes. Okay, same with class size in oh wait, class size should be different, right? Because that's what we're comparing. So we want small to be smaller than the other two. So that's fine. That's basically our outcome variable. And then, oh my God. And then percentile score in kindergarten is also different. Oh, okay, well that's our outcome. So this is 5 and 6. 5 is our like our x variable, our explanatory, and y is our outcome. So you can see that just before running any regressions, we see that the smaller class size does have a a much larger average test score outcome than the bigger groups. So that's interesting. And that sort of supports the argument that smaller class sizes is beneficial. But that's just looking at comparing the means. So yeah, the only concerning thing then is this attrition rate. Oh. I'm just going to re-explain my p-values because it wasn't really clear. Okay, so remember, when we have p-values, we always consider things statistically significant when the p-value is smaller than 10, 0.10, right? That's our statistical significance. So we usually think of p-values in 3 levels. We think of p-value at the 1%, the 5%, and the 10%. So the 1% level is the most statistically significant. That's your confidence interval of 99%. And then your 5% statistical significance is the second highest, and that's with your confidence interval 95%. And then your statistical significance of 10% is the confidence interval of 90%. So I'm only speaking whether it's statistically significant at the 1, 5, or 10. So for example, I say free lunch, this variable, you see the p-value is 0.09, right? So that's statistically significant. I say at the 10% because it's smaller than 10%, but it's not smaller than 5%, so it's not significantly significant at the 5%. So this free lunch, the difference between the groups, it's a joint p-value that tests the difference. We find that it's 0.09, which is statistically significant at the 10%. So you guys tell me, what would this attrition rate variable, what is it statistically significant at? %, exactly. Yeah, exactly. Good job, guys. So smart. It's 5% because it's smaller than 5%, but it's not smaller than 1%. So it's only statistically significant at the 5% level. And then for the outcome variables, the 5 and 6, we see that their p-values are 0.00. So that's statistically significant at the 1% level. This p-value is different between the treatment and control group only. Yes, but you see that there's 3 groups, so they're using a joint p-value for all 3 groups. So they're saying that the control groups are both the large class size and then the large class size with AIDS. No, not AIDS. Yeah, AIDS. I'm thinking of AIDS like we were talking about on Monday. I'm like, wait, what? Yeah. So yeah, it's a joint p-value for all 3. Okay. So let's take our 10-minute break here and we'll meet back at 7:04. That's 10 minutes. Math. Okay. See you in 10 minutes. I'll be here if you have questions. Okay, we're gonna start again. Gonna start. Okay. So we were just talking about this balance table for the STAR experiment, and we said that this attrition rate is not balanced between the three groups. The small class size is the treatment group, and then the other two are the controls. So we can see that the regular and the regular age group, they have higher attrition rates, which could create bias in our estimate if it's not random what type of kids decide to drop out of the experiment. Yeah, we talked about the balance and the attrition rate. Okay, this is the output table. As you can see, there's 4 columns, and they all represent different specifications. Okay, so what they do is they have the small classroom size as the main variable, and then in each specification, they're controlling for the regular aid class. So that's to say that they think it's comparable. So they want to remove that from the, I don't actually know why they would control. Weird. To me, I don't think they should control for it. It seems weird, but you know, that's what they're doing. I guess it's because they would only want to compare between the small class and then the regular class. So they're controlling for the regular aid class. Seems weird, but and then other controls include fixed effects for the school. So a fixed effect is when you're controlling, you're only looking within one school then. So within one school, there's multiple classrooms, so then we'd only compare within classrooms for one school. Why do you think we would want to do that? Well, it's because maybe there's differences between schools that would also affect outcomes. Maybe this school has a principal that's way better than this school, and that could also affect test score outcomes. There's so many factors about a school that could affect our outcome that we want to control for at the school level. We only want to compare between classrooms in one school because when you're comparing across multiple schools, there's a lot of other factors that could also affect the outcome. And so this just ensures that the treatment and control groups are more comparable. Yeah, it's always a good thing to put fixed effects at the group level. We'll talk about that more in the diff and diff section, but even in a randomization, it's not a bad thing to do. Okay. And then other controls include this free lunch variable, girl variable, so equals to 1 if the student's a girl, the white Asian variable we talked about. And then other things include teacher experience. So if one teacher is more experienced than the other, that could also affect the student outcome besides just having a small classroom, right? So if there's differences in teacher experience, that's a good thing to control for because it could very well affect the test score outcomes. And then master's degree is obviously for the teacher, not the students. If you have a master's in kindergarten, you are a freaking genius. And I don't think that'd be possible, but you never know. Okay, so looking at the results then, we're really interested in the effect of small class on our outcome, which is test scores. Okay, so you see that across all 4, our results are very statistically significant. You can check by dividing the coefficient by the standard error, right? And that gives you a t-value, which you can compare to our critical value. and that tells us whether our results are significant. And all of these are, even though they don't include stars, don't be fooled, it's still significant. You always want to check if there's no stars, because not all authors do that. So I know some of you might be used to just, oh, if there's stars, it's significant. If no, that it's not. Sometimes it's significant, they just don't put stars, so make sure you're looking at the standard error to check. Please, por favor. Okay, so yeah, all of these are like largely significant. You can see the effect size is large too, so the variable or the specification with the most controls, they see an increase in average test score for the small classroom size by 5.37 points. So someone asked to compare only small and regular class. Would you get the same results if you instead control using the regular aid class? So I guess by adding the regular aid as a control, it's controlling for both at the same time. So it's in comparison to, I guess, comparing to the, wait, let me think about this. Okay, well, so small class is a dummy equal to 1, right? So you're either a small class and that small class will equal 1, or no otherwise, so your regular class. So in that sense, the treatment variable is comparing small to regular, but then by controlling also for the regular aid class, you're also comparing to the regular aid class as well. So the authors are comparing to both at the same time, but they don't actually compare one-to-one small class to regular aid. And I suppose that results would be different and that they should do that, but they don't. They only compare it to both at the same time, which to me is a weird specification, but that's what they do. This is also really old paper, so I mean, the methodologies like these regressions are kind of weird to me for a randomization. I think it would be a bit different if it was the current paper. Like it's just a bit out of date. But yeah, you can see that the effect is really positive and large, especially when you're comparing to the effect of having a regular classroom with an aid. So this variable, regular aid class, is the effect of kids going to a class that is regular size, oh my god, I can't see, regular size, but with a special helper to help all of the students that need it, the extra help. So when you look at the effect of belonging to that classroom, it's actually relatively small. You can see it only increases average grades by like 0.12, 0.50, 0.30 compared to like a full 5 or 4 points in the first small class group. So there is a noticeable difference in effect size between the two groups. Any questions on that results table? Okay, also, I mean, this doesn't really matter too much for our class in terms of impact evaluations, and I'm sure you guys covered it in econometrics, but who can tell me what the R squared is? I mean, I rarely look at it, but it is good to know what it is. Okay, I'll say it. So the R, oh, wait. Yeah, Santiago says the variance explained by the model. Exactly. It's the, yeah, Nicholas too. What part of the variation of X is explained by I? Yeah, exactly. So how much of the variation on our Y variable is explained by X? And it's not really useful in absolute terms. Like we're never in economics going to have a super high R squared. And that's because in economics, we're looking at the economy, and so many things will like always explain your Y. So it's rare to have a large R squared. But the value to me of an R squared is being able to compare between different models, right? So if you're looking at adding fixed effects or other controls, you can see how it improves the explanatory power. And even better than that is because I know like a lot of junior economists will just try and increase the R squared by just adding a bunch of variables, because then you're for sure going to explain more of why somehow. But R squared adjusted adds a penalty for each variable you add, because you don't want to just add a bunch of variables that aren't doing much or don't make much sense in your equation. So looking at the R squared adjusted is actually better than the R squared, but it can be an indicator of how well you're fitting the model. Okay, that was a little random, but this is randomization, so may as well talk about random things. Okay, so yeah, we can see from the table before that smaller class sizes does have a positive effect and statistically significant effect on student test scores. In that case, the value is low. Yeah, so in that case, the R squared is pretty low for sure. So yeah, this is what the authors find in this result is contrary to what previous literature found, right? When previous authors used retrospective analysis, they found the opposite results. Well, not the opposite. They found that class size doesn't matter at all, that if you have a smaller class, it doesn't increase test score outcomes. Clearly, by comparing that to randomization, we can see that their evidence is likely to be biased, and that bias is likely being driven by the fact that weaker students, that lower ability students, are being put in the small class size to get more attention. And so then when you compare small class size to large class size, the outcomes, you don't really see an effect. But when you're able to randomize so that your characteristics or the students' like demographics in general, they aren't determining whether they go into a small or large classroom. It's being random. So that's what allows us to find causality. And then using the attrition argument, remember how we were concerned about the variable attrition rate because it was larger in the comparison group than the treatment group. So the big class sizes had larger attrition than small class sizes. The concern there was that then we would estimate a larger test score outcome for the control group, right? Because then if you have a control group and the lowest ability students are just dropping out of the experiment, then the average shifts up towards the high students. So then we're saying the control group, the average is higher, and then compared to the treatment group, our estimate would be understated, right? Because the true effect should actually be here, but then we're estimating a smaller effect. So our estimate is understated. Does that make sense why it's an understated estimate? Or no? I just want you guys to understand how to know when an estimate is understated or overstated based on the type of bias that we see. So for example, if the treatment group for some reason, their average outcome increases compared to the control group for some sort of bias, then our estimate will be overstated. But when the control group, their average increases compared to the treatment group for some sort of bias, then our results will be understated because the control group's shifting up due to some sort of selection bias. And then it could also be understated if the average of the treatment group shifts down for some reason too. So maybe the high ability students for some reason leave the experiment in the treatment group. So I want you guys to be able to understand when a given bias, if we have a bias in our estimate, what direction that would push our estimate. Is that clear? Yeah, I can repeat that. Okay, so we always have our estimate, and within randomization, it's probably good. If our assumption of randomization is good, then we have no problems. However, if there's some sort of characteristic that is not balanced between the treatment group and the control group, so in this example, attrition, that was larger in the control group than the treatment group, then we might have a problem if that biases our estimate somehow. So if we have a variable that isn't balanced, that biases our estimate, it's important that you're able to understand what direction, whether it's upwards or downwards, that variable is biasing your estimate. So you need to be able to figure out which way it's biasing your results. And usually you figure that out through economic reasoning. So we can just work through this one in this case. We talked about how attrition rate is higher in the control group. And think of what the control group is. It's a bigger class size. So then we're concerned that in bigger class sizes, students get less attention. So only the strongest students, the smartest students, can survive. They are the only ones that are able to keep up with the large class size. And therefore, the lower ability students have to leave the experiment. The lower ability students are the ones leaving. When it's not random what type of students leave the experiment, then we're recreating bias in our estimates. We had a randomization, that's great. Afterwards, if students drop out and it's systematic, there's bias. So we think that this might be biased because we have these low ability students that we think are leaving the experiment more than high ability students in our control group. And that would mean that since we have our low ability students leaving the experiment, the average test score outcome for the control group is actually going to go up because we don't have data on the low ability students anymore. We only have ability, oh my God, I can't speak. We only have data on the high ability students. So then the average test score outcome of the control group seems higher than it should actually be. And then when we're comparing the control group average outcome to the treatment group average outcome, the effect size between treatment minus control, it seems smaller than it actually is because our control group outcome got pushed up for this bias. I don't know if that makes sense or if it's completely confusing. Okay, good. So yeah, just being able to look at different cases or experiments, and when there is a variable that isn't balanced, you guys need to think about how it could affect your outcome and then how it would affect your outcome. So it's the two factors. Wait, what did I say? I said how it was. How it would affect your outcome and in what direction. Whether it would affect it upwards or downwards. Right? Because our estimated difference between treatment and control group is a number, right? So would this bias make our estimate bigger or smaller? Yeah. So if characteristics affect positively the outcome, that would have overstated and vice versa. Yes. So, well, it depends which group it's affecting and in what direction. So, for example, if this is a characteristic that's biased and it's higher in the treatment group and it will positively affect our outcome, then we would expect our effect to be overstated. Yes. Okay. But if this is a positive effect and this characteristic is higher in the control group, then we would expect the control group average to be higher, the outcome in the control group to be affected. Then when we subtract the outcomes between the treatment group minus the control group, the effect would be understated because we're actually pushing up the average of the control group. So we don't, either way it's bad. But you need to think about what group is affected and then how the variable affects the outcome, which will determine whether the outcome goes up or down for either group. Yeah. It seems super confusing, but it's just, I think you guys like have a good intuition. You guys are all in your 7th, 8th, 9th siglo, so I think you guys do understand how variables would affect your outcome, and then you just need to consider what group it affects next, and then based on that, how it affects the averages. Okay, so now we're just going to look at regression, the regression format of our CTs. So when we're working with data in Stata or R, we're always, when we're running analysis, we're putting it into a regression format. That's how we analyze our data. So as I said, when we put our randomization into a regression, we're able to use OLS, just a simple linear regression, right? Because we're saying that with randomization, our outcome variable is only a function of our treatment, right? Because the treatment is the only difference between the two groups to begin with. So when our treatment is the only difference between the two groups, we don't need to worry about controlling for anything. So then we can just write y as a function of our constant term plus our treatment dummy plus our error term, right? And di is our dummy for treatment. And so following this, we can interpret each coefficient differently. So for example, alpha is our constant term. That's our baseline outcome if there's no treatment. So the expected value of y, 0i. So that's your baseline health or whatever our outcome variable is. That's our health or y before we receive treatment, right? And then our rho, this is rho. This is our causal effect of interest. So for example, for individual I, it's the difference between y1i minus y0i. I mean, in a group example, it's actually the expected value of y1i minus y0i because we're looking at groups, so we need to look at averages, right? So this is for an individual, but in actual examples of randomization, it would be the expected value y1i minus expected value y0i because it's the group average, okay? And then our error term, that's eta, that's gonna capture our, this is for each individual, the difference between the individual baseline outcome relative to the mean, right? So for each person, we have an eta I, the error term here, and that's my baseline outcome minus the average, right? So maybe I'm healthier than the average person, so 5 minus 4, 1. So we have these differences for each person in the sample, right? So the thing is we want eta I to be 0 on average. And it will be with randomization, right? So basically we can derive the following conditional expectations from the equation before, just in expectation terms. So then we have two different equations for the treatment group and the control group. So here we have the expected value of our outcome given di equals 1. So that's our outcome given you're in the treatment group. That's alpha plus rho, so our baseline outcome plus our treatment effect, plus the expected value of eta I given di equals 1. So you're basically your baseline outcome minus the average given you're in the treatment group. And then the exact same thing for the control group. So we have our outcome as a function, or given by, oh my God, our outcome with respect to CI equals 0. So your outcome variable, if you're in the control group, the function of the baseline outcome plus the expectation of your A to I for the control group, given that you're in the control group. But remember what we talked about at the very beginning of this class, that the expected baseline outcomes between the treatment group and the control group is 0. So there should be identical. Saying that, we know that these two should be equal, right? So when we put these two together, for example, we want to know the difference between these two lines. So we're subtracting the bottom line from the top line. That's what we have here. You can see, oh my God, I'm using my finger, but you can't see where it's going. I'm so dumb. So the expected value of yi given di equals 1 minus the expected value of yi given di equals 0. These are these two terms. We're just subtracting them. Treatment minus control. That always is the treatment effect that we're after, that we want, right? That's what our row is trying to give us. So that gives us our row, which is our treatment effect of interest. That's what we want to obtain, plus the selection bias term. But look what the selection bias term is composed of. It's the subtracting of these two terms right here. The expected value of eta given di equals 1 minus the expected value of eta given di equals 0. And we know that these etas are the difference between my baseline outcome minus the average. But since these groups are random, they should be equal on average. So then they're just going to be equal, and then subtracting them will be 0. Right? So that's why the selection bias term is erased, just canceled out, and we're only left with the treatment effect. Questions on that, on how we can erase the selection bias term? Okay, so I know it's harder because normally I would write this out on the board, but we're doing this over what's called Zoom. So what I would like you guys to do, just for your own benefit, is just practice writing these out. So just write out these two lines, for example, and then just subtract them, and then you can break apart each term. I mean, it's super simple, but it might help with your understanding of the selection bias process and randomization. Okay. We already talked about internal validity a bit. We're just going to talk about internal and external validity now. Okay. Also, tell me if I talk too fast. I know I really talk fast, so let me know. Okay. Internal validity, we talked about this. So, I'll ask the question. So if we suspect it's not canceled, then we have to analyze whether the effect is under or overstated. Yes. In practical terms, yes. We don't need to suspect, we can test this, right? So we're saying that randomization eliminates the selection bias, but that's given the independence assumption that our treatment status is independent of all of our baseline characteristics. So we need to go back and check the baseline characteristics of the treatment group and the control group using our table, right? So if in our table we find that some variables are not random across the two groups, or to say that they're not balanced, so maybe one group, they're older than the other group, and it's statistically significant, then we need to see, yes, how this age variable, for example, affect our outcome? And in what way would it, and then what group is it affecting? And that will tell us whether the effect that we find is over or understated. And that's important because you need to find ways to ensure that you don't have bias in your estimates. So if it's really overstating the effect, that's concerning. So you should try and control for it, or, just acknowledge it that it might be biased somehow. Okay. No problem. Okay. Internal validity means that the estimated impact of the program is basically net of all other potential confounding factors. So that's a really fancy way of saying that we find causality, and that when we find the effect, there's no other factors affecting our outcome that is being estimated in our effect. So basically, we have found a valid counterfactual, and we are estimating the true impact of the program. So given that, that basically relies on the fact that our assumptions of our methodology are true. They're holding true. That means we have causality, right? So it depends on what the methodology you're using is. In the case of randomization, it's that randomization was successful, and we have the independence assumption holds. So that ensures our internal validity. When you guys are writing your thesis, it's really important that whatever methodology you use, you try and show some way that your paper has internal validity by trying to test your assumptions somehow. So throughout each chapter, we will talk about the key assumptions of your methodology that we're talking about and ways to be able to show that they're true. Some assumptions aren't testable, like diff and diff doesn't have a testable assumption, but there's ways to kind of comfort the reader. You want to argue your case. Like, economics isn't just black and white. There's a lot of persuasion that goes on in assumptions. So it's really important that you know your strengths and weaknesses of your methodology, and you try and push up your strengths as much as possible and account for your weaknesses when you need to, right? So there's ways to kind of address things that aren't good about your research. But yeah, anyways. Like making robustness checks. Yes, Susanna, exactly. Robustness checks are great because they can kind of confirm that your results are true and not just out of luck. So if you can do a robustness to show, no, my results are consistent when I use this other method, then it really looks good for you. Also, falsification tests. So I don't know if I talk about this in regression or in RCTs. So a falsification test would be checking for a treatment effect. So you use your same treatment dummy, but you test it on a period before the treatment group receives treatment. And that falsification test, you want it to be insignificant, right? Because if it is significant, then you're saying, we find a treatment effect before they even receive treatment, so that doesn't make any sense. So yeah, like if you check it on the period 1, where the treatment group and the control group are randomized, of course, if they're perfectly randomized, you'll get no effect because there's no difference in outcome yet. But if you do find an effect, it's bad because you're saying that there's a difference in outcomes even before they receive treatment. So, for example, a falsification test could be a good thing to add to a randomization paper along with a balance table. What was the first test? What was the first test? Oh, like falsification test? I'll write it. I think that's all I said. And then a balance table. Oh, sorry, I messaged privately. Oh, I hate this. Yeah, so those are two ways for randomization to just show that your randomization was successful and that you have no factors that are confounded in your estimate. Okay. Secondly, we have external validity, which is more important from a policy standpoint because we want to know that the results that we find, we're able to find similar effects in other populations. That's what makes our research generalizable. So reading the paragraph, external validity means that the evaluation sample accurately represents the population of eligible units. The results of evaluation can then be generalized to the population of eligible units. So we use random sampling to ensure that the evaluation sample does accurately reflect the population, so that impacts identified in the evaluation sample can then be extrapolated into the general population. So for example, if only a certain subgroup of the population are selected for randomization, the true treatment effect may not then be representative for the whole population. So if we look at the effect, I don't know, we're looking at like giving textbooks to kids, but we only give them to the smartest kids, maybe we'll see a lot larger treatment effects than if we gave it to an average population. So then although the treatment effect, it may have internal validity because our randomization is satisfied, it might not have external validity if the subpopulation isn't representative of the population at large that would receive this program. So yeah, we need external validity because we want our results to be generalizable, which is really important in the policy application of our research. Okay. And also because we're interested in not just one little village, we're interested in how this treatment could affect maybe all poor people or whatever. So you don't want it just to be true for one small population when you're doing research. So this is a nice little picture that kind of explains external versus internal validity for randomization specifically. So you can see it has different steps. So step 1 is define eligible units. So here you can see the dark is ineligible and then the light is eligible. Oh wait, no, that's the world. I get it. Oh, I see. Never mind, I'm confused. That's the world. Okay. So this car guy is ineligible and these people are eligible across the whole world. Okay. So then within that, you have external validity if you take a general sample of the full population. So you can see, suppose these are like people of different culture or something. There's people represented from each culture in the small sample. So that ensures external validity because then you can say the average characteristics of this group are similar to the average characteristics of the whole group, which is what we need for generalizability. And that's usually done through random sampling of the full population. But sometimes that's hard in experiments, so you need to be careful. And then the internal validity is randomly assigning people to treatment and control, right? That's internal versus external. Any questions? If not, I will see you all on Monday. Have a great weekend. You can email me if you have questions. Good job. Thank you for coming. Adios. Okay.